Welcome back, everyone. Let us go ahead and move on to the next section in Chapter 20, in which we are going to discuss concepts associated with blood flow and blood circulation. Now, here you can see a simplified diagram that shows the circulation of blood throughout the body. You'll recall if you start with deoxygenated blood in the right ventricle, that's going to pump that deoxygenated blood into the pulmonary circuit, through the pulmonary arteries and into the lungs, where gas exchange is going to occur. The blood will become oxygen rich, return to the left side of the heart through the pulmonary veins. The left ventricle will pump a stroke volume of oxygen-rich blood out into the systemic circuits where gas exchange will occur again. Oxygen will be delivered to tissues, and at this point, blood will return to the right atrium of the heart to start this process again. Now, the two things we want to pay attention to here are the cardiac output, that refers to the amount of blood delivered from the left ventricle to the systemic circuit every minute, and the venous return, that is the amount of blood returning to the right atrium of the heart through the vena cava, coming back from the systemic circuit every minute. Now, you can probably imagine that because this is a closed circuit, that the cardiac output must always be equal to the venous return, which again should always be equal to the rate of blood circulation. So that's just good accounting, right? The amount of blood being pumped by the heart has to equal the amount of blood returning to the heart. Well, this is going to have some important consequences for blood flow and delivery to tissues that we're going to see later on. Naturally, if the cardiac output or the venous return changes, the other has to change proportionally. And we have also discussed that a major determinant of blood flow from place to place in the body is going to be those pressure gradients or pressure differences between two different points. That's ultimately going to be one of the things that determines the rate of blood flow between those two destinations. Not the only determinant, but one of the major ones. So here's a very similar looking diagram in which you can see venous return going back to the right atrium in blue and cardiac output coming from the left ventricle in red. So if everything else is equal, and everything else is something that we'll discuss fairly soon, if the only thing that we're considering here are pressure gradients, then the idea is that the greater the difference in pressure between the 2 points is, the quicker the blood flow will be. So if you make an assumption that the pressure in the vena cava is 0 millimeters mercury, it's not quite going to be that low, but it will be pretty low. If you assume the pressure is practically non-existent in the vena cava as the venous return makes its way back to the right atrium, and if you assume the mean arterial pressure coming from the left ventricle is about 100 millimeters mercury, then that is a total pressure difference of 100 millimeters mercury. So that amount of pressure difference is going to help drive the blood flow all the way through the systemic circuit and as it makes its way back to the right atrium. Now, if the pressure gradient were to drop, then naturally that is going to have consequences for both the cardiac output and the venous return. So here's a question for you. What do you think would happen to the volume of the venous return if the mean arterial pressure decreased? We're talking about this number right here. And also, what would happen to the volume of the venous return? What would happen to that if the venous pressure increased? We're talking about this pressure right here. And you might also be thinking about what would happen to the cardiac output. Remember, the cardiac output refers to the volume of blood being delivered to tissues every minute. So you can appreciate, hopefully here, based on your thinking about this, that any change to pressure at locations in the body can absolutely affect both the cardiac output and the venous return. So in both cases, the venous return would decrease, and that would also cause the cardiac output to fall as well. And that being the case, you're risking having poor perfusion of major tissues like the brain and the heart and skeletal muscles. So I mentioned that the pressure gradients are not the only determining factor involved in blood flow to tissues. All the other factors combined, and we'll talk about what they are individually here soon, all of the other factors combined make up what's called resistance to blood flow. And what we're going to see here in this little thought exercise is that when you consider how blood gets divvied up to all the different organs like the brain and the heart, the liver, skeletal muscle, the skin, the kidneys, the GI tract, when you consider how blood gets distributed to all these different locations, it's not necessarily going to be an equal distribution. Now, this idea of resistance to blood flow, if resistance to blood flow was equal in all of those different locations, and if all of them experienced an equal pressure gradient on either side of their capillary beds, then yes, blood flow would be equal between all of them, and the whole blood supply would be equally distributed to all tissues. However, what we're going to see here is that even if the pressure gradients are all equivalent, these different organs and tissues experience a very different resistance to blood flow when you compare them to one another. And as such, these different tissues are going to be exposed to higher rates of blood flow compared to others which may experience lower rates of blood flow. The more resistance to blood flow a tissue or an organ experiences, the less of a fraction of the total blood supply it's going to receive. Now, if you look here, don't worry too much about the milliliters per minute. Remember that it has to add up to somewhere between 5 and 6 liters per minute, because that at rest, that's going to be about how much your cardiac output is going to be. Pay attention to the percentages. You can see here that some tissues and organs receive a greater supply of the blood at rest. And now this is important, at rest. We'll see how this sort of thing changes with exercise later on. But at rest, you can see that the vast majority of the blood supply goes to the GI tract, the kidneys, the brain, and skeletal muscle. Later on, we'll see that it's not so much at rest that skeletal muscle needs this much blood, it's just that skeletal muscle makes up such a significantly large portion of your overall body mass that it just so happens to receive a large portion anyway, even though its overall need is not very high. Some places like the heart and the skin receive a much lower portion of the total blood supply when you compare them to other places. So the way we can kind of explain this is that the higher the percentage that you see in this chart, the less resistance to flow that tissue or that organ experiences. So what may be a sizable pressure difference that may exist to drive blood flow into the skin or into the heart, if there is a large degree of resistance to blood flow in that organ, then blood flow is not going to be as high as the pressure gradient might have you believe. Okay, so let's kind of pick apart what actually determines this resistance to blood flow. So resistance to blood flow is a completely separate issue from these pressure gradients as we just discussed. But the resistance to blood flow has several different components to it that we're going to discuss here. So to put everything together, both the pressure gradient and the resistance issue, let's introduce Poiseuille's law, which is a physical law that dictates the flow of a fluid through a hollow tube, like blood flowing through a vessel. Now, this equation is going to seem extremely complicated at first glance, but I can make you feel better about it by telling you that, number one, I'm not going to have you do any calculations with this, and number two, we can actually make sense of this equation once we define what the terms are. So there's a lot of good information that we can derive from this. Number one, if you look at delta P, blood flow equals delta P up there in the numerator times everything else. The fact that delta P, the pressure difference between the 2 points in the circulation, because that is in the numerator, that tells us that the higher the pressure gradient is, the better the blood flow is going to be between the 2 points. But we already knew that, right? Number two, the greater the distance between the 2 points, that's the L down here in the denominator, and the smaller the radius of the blood vessel is, that's R right there, the more resistance to flow there's going to be. Because radius is up here in the numerator, as that number gets smaller, the blood flow is going to get worse. Because length is in the denominator, as the length gets bigger, the blood flow is going to get worse. So what that tells us is that blood flow is really going to meet resistance. There's going to be a lot of resistance to blood flow in a narrow blood vessel and a blood vessel that is very, very, very long. Even if the pressure gradient is very big between the two different points at the end of the vessel. The more viscous the blood is, that's the Greek letter eta here, the more viscous the blood is, the more resistance to flow there's going to be. So we talked in chapter 18 about how blood is fairly because blood is fairly viscous, that's going to cause a resistance to flow on its own. And we said that that's going to underlie the importance of there being a strong pumping mechanism when it comes to getting blood circulating. But thankfully, the viscosity of the blood is not something that should change too terribly much in any case, so we shouldn't have to worry about it too much. Okay, so let's look at some of the bottom line here. Vessel length and blood viscosity should be fairly constant on a case-by-case basis. Now, when it comes to vessel length, you will see differences between the left and the right side of the body since the left ventricle is tilted towards the left side of the thoracic cavity. So, for example, if you're measuring blood flow in the left arm versus the right arm, it takes a greater blood pressure to drive blood flow through your right arm than it does your left arm, because the vessel length is greater on the right than it is the left. But if you're just considering a case-by-case basis, vessel length is not something that we'll usually have to think about too much. So ultimately what this is going to tell us is that the two biggest determinants of blood flow, the most dynamic determinants of blood flow, the things that will change most frequently and have the greatest effect on how blood flows through an organ or a capillary bed, it's going to be the pressure gradient, delta P, and it's going to be the radius of the blood vessel. In other words, when we need to make adjustments through homeostasis for delivering blood to different tissues and organs, altering those two different things is how we're going to get the best effects. Now look at this example right here. Ultimately, even though the pressure gradient is going to be a major determinant, the greatest effect we can have on blood flow we are going to see here is through vasoconstriction and vasodilation. Through vasoconstriction and vasodilation, we can and we will see very, very, very significant effects on the radius of the blood vessel and therefore effects on the blood flow. Now pay attention to Poiseuille's law right here. The radius is raised to an exponent, so it's raised to the fourth power, meaning that if you were to double the radius of a blood vessel through vasodilation, you're not going to double blood flow, you're going to increase blood flow by a factor of 16. So 2 to the fourth power would be 16, correct? 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. Similarly, with vasoconstriction, if you reduce the radius of the blood flow by a factor of 2, you're going to reduce blood flow to that organ by a factor of 16 as well. So that is the unique nature of the radius being raised to the fourth power here. You're going to see a much bigger effect than you might otherwise believe. So ultimately what this tells us, and this fits in perfectly with discussions we've had before on the autonomic nervous system and vasoconstriction, vasodilation, you can drastically increase or decrease blood flow to an organ just through vasoconstriction and vasodilation. You don't even really need to be messing around with pressure gradients. So if we look at kind of an overall roadmap of blood flow through the circulation, we can kind of make sense of these resistances and how blood gets divvied up into different tissues from the knowledge that blood flows in parallel to organs, meaning that from the aorta going into the systemic circuit, the aorta branches off into many, many, many different arteries, with each minor artery tending to serve just one major capillary bed. In doing it this way, blood flows through one organ and then directly drains into the vena cava. We don't necessarily have to have blood flowing from organ to organ to organ to organ. That would obviously not work because all the nutrients would get sapped out of the blood from the first organ, leaving nothing left for the second organ. So it's a good thing that we have blood flowing in parallel rather than in series. So as we said before, each one of these capillary beds and each one of these organs that you see here is going to experience a different level of resistance to blood flow. In chapter 19, when we talked about the autonomic nervous system's ability to regulate the cardiac output. And we talked about this in terms of total peripheral resistance. So the sum of all those individual vascular resistances on average makes up the total resistance to blood flow in the circulation, which is going to be a determinant of both the cardiac output and the venous return. So this is going to mean that through the actions of the sympathetic division of the autonomic nervous system, remember the parasympathetic division does not participate in vasoconstriction and vasodilation, we can strategically vasodilate some arterioles and vasoconstrict others to make sure that the most important organs are getting the blood supply at the right times. And organs that don't necessarily need blood supply, like the kidneys and the GI tract during stress, they can do without having as much. Okay, so what are some ways that the body can actually regulate blood flow? The first one here we have already talked about many times before. This is called extrinsic regulation of blood flow. This refers to the actions of the sympathetic division in conjunction with the endocrine system, that's epinephrine being released from the adrenal medulla, to stimulate the smooth muscle of the tunica media of arterioles to achieve vasoconstriction and vasodilation. And because of Poiseuille's law that we just saw, we can see this is a very, very effective way of achieving regulation. A second way is through what's called intrinsic regulation of blood flow. This refers to built-in mechanisms by which organs can regulate their own blood flow without the need for outside influence from the sympathetic division of the autonomic nervous system. These tend to happen through either metabolic changes or myogenic changes, meaning that in a sense the smooth muscle can regulate itself in conjunction with that own organ's ability to sense its need for nutrients. A good example of this is the brain. The brain always needs to be receiving a certain portion of the blood supply, so we would not want something to go wrong coming from the autonomic nervous system that would cause the brain to not get its fair share of the blood supply. So it's able to determine for itself how much oxygen and how much blood it actually needs. So in this case, the smooth muscle in the arterioles that surround the brain can produce their own vasodilation and vasoconstriction effects in response to the oxygen needs of the tissue they service. So if we focus just a little bit more on extrinsic regulation of blood flow, so that's norepinephrine and epinephrine effects, we've already seen in chapter 19 how these can increase the cardiac output both through regulation of the heart rate and the stroke volume. So we can also now understand that it can have effects on total peripheral resistance in tissues through vasoconstriction and vasodilation. So we can kind of put this all together with observations we've made throughout the semester that in the fight or flight response, you don't need blood flowing into non-essential organs like the kidneys and the digestive tract and the skin. It's best to make sure that that blood is being delivered to the skeletal muscle and the brain. So a little bit more detail on this. So we said that blood flow does need to improve to organs that are essential to the flight or fight response, so brain, skeletal muscle, and things like that. Not that this is super duper important, so I don't like to really focus on exceptions to the rule, but this is sometimes going to involve sympathetic postganglionic neurons that happen to release acetylcholine as their neurotransmitter rather than norepinephrine. Now, I know we usually associate acetylcholine with parasympathetic fibers. This just happens to be one of those exceptions to the rule, just like what we saw with sweat glands. So don't worry about this exception too much, but this is just a little bit of extra information just to kind of make sure you see the whole picture here. So here you can actually see all the different sympathetic effects on vascular resistance and blood flow throughout the body. So again, these are all going to be mostly sympathetic effects. Parasympathetic effects are not really going to be direct effects through nerves, but rather indirect effects through that eventually are going to lead to hormonal effects, such as what you see with angiotensin II, antidiuretic hormone, and some of these paracrine regulators down here. Direct extrinsic effects are going to always come from sympathetic effects rather than parasympathetic effects. Okay, so let's start to talk about how blood flow can change to different tissues in the body when you go from a state of rest to a state of either stress or exercise or something associated with the fight or flight response. So we've discussed how peripheral resistance in some tissues and organs are just different compared to others, and as a result, some tissues get a better supply of the blood than others. So if you look at this diagram here, the blood flow to a particular organ, in this case we're looking at skeletal muscle, increases by a factor of 20 when you go from rest to a state of heavy exercise. So if the skeletal muscle gets about 1/5 of the total blood supply when we are at rest, it's going to get something much greater than 50% later on, as a consequence of not only the cardiac output increasing, but also vasoconstriction and vasodilation directs a lot of that extra blood flow to the skeletal muscle. So we've said that skeletal muscle has quite a very high peripheral resistance, but because there is so much muscle mass, even at rest it still takes up somewhere between 1/5 and 1/4 of the total blood supply. Intense exercise will obviously activate the sympathetic division. Alpha adrenergic receptors in the skeletal muscle, vascular smooth muscle, in the vascular smooth muscle of the kidneys and the GI tract will divert a lot of that blood flow away from them and towards the skeletal muscle to get extra blood delivered to those needy tissues. Now here is a diagram where you can actually see this actively occurring. At rest, the entire blood supply you can see gets divvied up between these different muscles, and like I said, skeletal muscle only gets about a fifth of the total blood supply. Well, during exercise, you can see how some of the distribution changes so that we can deliver the vast majority, about 80 to 85% of the total blood supply, specifically to skeletal muscle, which of course is using a lot of ATP to maintain contractions. Now, look at this diagram real quick. Other than skeletal muscle, which tissues have the most gain from blood flow following sympathetic stimulation? And really what I want you to focus on is which tissues lose out the most. So we know that skeletal muscle has the most to gain, but which tissues are losing the most blood flow when we go from a state of rest to a state of exercise? So like I said, obviously the gain is coming at the level of skeletal muscle. The ones that have the most to lose, as we have referenced several times this semester, are going to be the kidneys and the GI tract. The kidneys go from 20% down to about 2 to 3%, and the GI tract goes from about 1/5 to 1/4 down to 3 to 5%. So we drastically cut off the blood supply to those organs by using vasoconstriction, strategic vasoconstriction, I should say, just at those locations. So all that blood that otherwise would be going to those locations can be rerouted to the skeletal muscle. And here you can see some different effects, whether they increase, decrease, or do not change at all in response to moderate exercise. Now, from chapter 19, we of course understand that the cardiac output and its constituent factors, the heart rate and the stroke volume, will all increase. Total peripheral resistance will decrease as a function of decreasing resistance to blood flow in the largest major tissue in the body, being skeletal muscle. Resistance does increase in some other locations, but the net effect is that total peripheral resistance does decrease during exercise to get the blood flowing more easily. Blood pressure increases, and we will talk about blood pressure pretty soon. The end diastolic volume does not end up changing too much because the cardiac output increases and the venous return increases as well, so it's kind of a zero-sum game in that regard. Blood flow to the heart and muscles increases. Blood flow to non-essential visceral organs like the GI tract and the kidneys decrease as a consequence, of course. Blood flow to the skin increases as a means of expelling excess heat from the body through sweating mechanisms. And blood flow to the brain should be mostly unchanged. As always, like we said before, the brain receives its blood supply pretty constantly through myogenic and intrinsic mechanisms. So you can see here that there are many different factors that determine blood flow into a place like skeletal muscle. Not only should we consider things like cardiac output, which we discussed in chapter 19, but there are a lot of different effects on vascular resistance and how those things can change to improve blood to some locations and disimprove blood to other locations that are just not as important. Okay, that's going to do it for this video. Again, thank you very much for your attention. Next time, we are going to talk about actual blood pressure measurements and blood pressure determining concepts. So we will talk about that next time. I look forward to seeing you again. So long.